I'm going to talk about something that dovetails with what Max was talking about in terms of interpretable AI. So basically, I work at the intersection of neuroscience, machine learning, and physics. And there's great reasons for a new type of alliance between theoretical neuroscience and theoretical machine learning. And that's the following reasoning that was laid out in this, in this review article. Basically, we'd all like to understand how the brain works or how a neural circuit works, but what does that even really mean? A more proximal version of that question is we'd like to understand how the connectivity and dynamics of a neural circuit give rise to behavior. And of course, learning is important. We'd like to understand how neural activity and synaptic learning rules conspire to self-organize useful connectivity that subserves behavior. Now, the field of machine learning has generated lots of trained neural networks that accomplish very interesting tasks. And this raises a very important conceptual question. We know everything about these networks. We know their connectivity, we know their dynamics, we know their learning role, we know their developmental experience, yet we don't have a meaningful understanding of how they learn and work. And it's worse, we don't even have a benchmark for what such an understanding, once we finally attain it, would even look like. Right? So we outlined some thoughts in this review article here on that topic. So we've been thinking about these issues both in biological and artificial networks. Over the last couple of years, we've worked on several articles trying to understand both biological and artificial networks using ideas from physics. In fact, it's actually quite nice. It's a very nice theoretical playground where ideas from frontier topics in physics like non-incremental stat mech, dynamic mean field theory, random landscapes, random matrix theory, and so on can really play a role in shedding insight into these networks. I can't possibly talk about all of this work today, so I'm just going to tell you sort of two stories. One of these stories is how do neural networks generate a hierarchical differentiation of learned concepts in the same way that infants actually do. And if we have time, I'll also talk about how deep and recurrent neural networks can navigate high-dimensional synaptic weight spaces without getting stuck. Okay. So the first work is it was published recently in this PNAS paper, and it's joint work with Andrew Sachs and Jay McClelland. So here's the basic idea. What is semantic cognition? It's basically our ability to learn, recognize, comprehend, and produce inferences about properties of objects and events in the world, especially properties that are not present in our current perceptual stimulus. For example, I could ask you, does a cat have fur or do birds fly? And there's no cat or bird in this room to my knowledge, but you all know the answer to these questions. Right? Our ability to do this relies on our ability to form internal representations of categories in the world. We never see the same stimulus twice, so we form these abstract categories in our head. And these categories form the basis for perceptual decisions and actions and planning and so forth. Yeah. So how do we learn these categories? So a lot of work in psychology has shown that the way that infants learn categories unfolds in a hierarchical fashion. At an early age, even if you control for perceptual similarity, infants at a very early age will discriminate coarse categories like animals versus plants early on. And then later on, they'll be able to discriminate different types of birds from fish and trees from flowers, and then even finer scale distinctions, different birds, different fish, and so on. So they learn categories in this hierarchical fashion. And also, we know that there are some categories that are worth naming or are coherent, i.e. the set of all things that are dogs is a very coherent category, so coherent that we actually have a name for it. There's a myriad other categories that you could form in this world, but we just don't form them. These are the incoherent categories. For example, the set of all things that are blue. Psychological studies have shown that we tend to learn coherent categories and we learn them faster, and we don't even ever learn incoherent categories, so why? Okay. So my colleague, Jay McClelland, outlined a lot of these issues in this book, Semantic Cognition, and he tried to model these things using deep neural networks before they were popular, or more precisely, the first time they were popular, in the 90s and so forth. So during the parallel distributed computation age. So what he did was he had a toy universe of different types of animals and fish and plants and flowers, and he asked the network to learn to answer a whole bunch of questions about these inputs. And then there's this hidden representation layer that somehow has to represent these inputs in an organized way in order to answer these questions. And so what I'm going to show you is I'm going to show you the dynamical evolution of internal representations in this representational layer. Okay? And what you can see is this hierarchical unfolding of internal representations. Here's a multidimensional scaling plot that looks at the internal representations in a two-dimensional space that you can visualize that preserves distances in the higher dimensional space. And initially the network is random, so all the internal representations are in the center. Then what happens is early on, the animals separate from the plants, and then later on the fish and the birds separate, and the trees and the flowers separate, and then finally the individual items separate. So there is this hierarchical unfolding of structure in these deep neural networks, just like how it occurs in infants. Okay? And this is the same picture using a hierarchical clustering dendrogram. All right, so when I first saw this, I was at once astounded and also disturbed. I was astounded because these deep neural networks were behaving a lot like infants, but I was disturbed because we couldn't really understand why this was happening. Surely there must be a very simple principle that explains why this hierarchical differentiation of structure emerges naturally out of this deep neural network. Right? So this raises some theoretical questions. What are the mathematical principles underlying this hierarchical self-organization of internal representations? And also, what is a mathematical definition of category coherence, and how does it relate to the speed of category learning? There's a whole bunch of other phenomena that we handle in the paper, but I don't really have time to talk about all of that. So the way we decided to look at it was we decided to start analyzing the dynamics of learning in a deep linear network. Now, of course, a deep linear network is no more expressive than a shallow linear network because the composition of linear functions is linear. But the learning dynamics of a deep linear network is gradient descent on a highly non-convex error landscape and therefore is highly nonlinear. Just to see that, what we do is we feed inputs into this network. It propagates through two layers of weights, and there's a cost function that penalizes the discrepancy between the right answer and the answer to the network output. The cost function is quadratic, so therefore in the weights it's quartic. So gradient descent on this cost function will have cubic terms in the weights on the right-hand side. So if you write down these gradient descent equations, the actual equations don't really matter too much, but you just get a bunch of coupled nonlinear ordinary differential equations that are cubic as promised on the right-hand side. And we discovered exact solutions to these equations. And they can be described using certain properties of the input statistics. So basically, there's some training data which is a collection of inputs and desired outputs. Okay. That training data has an input correlation matrix, how correlated are these inputs across the training set, and an input-output correlation matrix, which tells you how correlated the input neuron is to the desired output here across the training set. Okay. We're just going to assume that the input correlations are white, and so what drives learning is the input-output correlation matrix that has dimensions the number of inputs by the number of outputs. Okay? This input correlation matrix can be decomposed via singular value decomposition, and that's what governs the network's learning dynamics. You can view the singular value decomposition of such a data matrix as projecting, so here's an example data matrix where you have a canary, a salmon, an oak and a rose, and certain properties like move, fly, swim, bark. This is the data matrix, and this is its singular value decomposition. These singular vectors can be viewed as input analyzers that project the inputs onto an internal representation space. These are the singular values, and these are feature synthesizers that synthesize the features. Okay, it turns out that this aspect of the training data is what drives the learning dynamics as follows. The exact solutions that we find tell us that the product of the weights will build up a time-dependent version of the singular value decomposition where it'll learn each singular mode according to a sigmoidal learning curve, where the larger the singular value in the training data, the earlier the learning will occur, and it's a very sharp, rapid transition. Okay? So basically, what this network does is, again, it builds up the singular value decomposition mode by mode. Okay, that's kind of the take-home message. So just to summarize, We'd like to understand how statistical structure in the training data seeps into the weights. This is an exact answer in this simple setting. The statistical structure is an input-output mode of the singular value decomposition. The strength of that structure is the singular value of the mode, and the time scale of learning turns out to be 1 over the singular value. And the network exhibits sudden developmental transitions where the network seems to do nothing for a while and then it suddenly learns in input-output mode. Babies do this in the same way. They'll do nothing for a while and then suddenly learn a new fact or a new category, right? Okay, but what does all this have to do with the hierarchical differentiation of concepts? Well, one of the issues in the previous work is they were looking at toy models. What we'd really like to do is we'd like to understand how probabilistic processes that could have generated our world, when fed into neural networks, gradually seep into the weights and learn the structure of the probabilistic process that generates our world. So to generate a generic hierarchical data set, we mimic the process of evolution to just have a branching diffusion process where we generate data vectors for each item, where you have an ancestral feature that diffuses down the tree and has a small probability of mutating. Okay, so then clearly two leaves on the tree, i.e. animals that are closer together in ancestry, will be more similar to each other in feature space. So this naturally generates hierarchical structure. And so now the question is, what is the singular value spectrum or decomposition of such data? Here's an example for the symmetric tree. It turns out the singular modes that have larger singular values make coarse distinctions on the tree. So for example, they're positive on all these nodes and negative on all these nodes. Singular modes that have smaller singular values make finer scale distinctions, say between this and this or between this and this. And then the lowest singular modes make individual distinctions between the leaves of the tree. Okay? So now when you put this all together, you get, we can compute the singular values and they match experiments and all that. But when you put it all together, you essentially have a theorem that any network of this form must exhibit progressive differentiation of structure on any data set generated by this class of hierarchical diffusion processes. Basically, network learns large singular values on short timescales given by 1 over the singular value. Singular values of broader hierarchical distinctions are larger than those of finer distinctions. And the input-output modes correspond exactly to the hierarchical distinctions in the tree. So when you put all this together, you actually get analytic formulas for these multidimensional scaling plots of how internal representations of the network evolve over learning. And as you can see, what we get in our simple toy model analytically mirrors basically what's going on in a much more complicated model. And of course, this is the difference between numerical simulations and theory. Hopefully, you'll agree that there's much more conceptual insight into what's going on now. So a simple proposal for what is a category is that a category is a subset of objects sharing a subset of features that are important for that category. But of course, this yields a conceptual Gordian knot that has bedeviled the field of category learning in psychology, is how does one then learn a category? Well, one possibility is you identify the objects that belong to the category, but then you need to know which features are important for the category. So for example, having seeds is important for being a fruit, but being red is not important for being a fruit. Right? The other possibility is you could identify the features that are important for the category, but how do you do that if you don't know which objects belong to the category? Okay? And again, some categories are more coherent than others. So we also looked into this, and we created a toy data set. So for example, here's my son when he was younger. He saw a pink unicorn, and he'd never seen a pink unicorn before, but he was kind of surprised by it. And we see a whole bunch of objects with a constellation of features in sequence one by one. Here's an example of a toy data set that consists of about 1,000 or so objects. Each object is specified by a column or a feature vector that has 1,600 features. Each feature can be either present or absent. Okay? If I show this data set to the simple deep linear network, what you can see is that the evolution of internal representations look like this. There's a whole bunch of objects at the center that didn't get learned. There's a large set of objects that got learned quickly, and then, this one, and then more that got learned a little bit later, and a fewer that got learned even later, okay? And it discovered these three categories. We can look inside the weights of the neural network and reorder the, use the learned knowledge and the weights to reorder both the features and the objects, and if you do that, you'll see that you actually had three categories hiding inside this data set. I just did a permutation to go from the previous slide to this slide, where these three categories are indeed a subset of features that tend to co-occur across a large set of objects. So it discovered this bathed within this sea of irrelevant features and irrelevant objects, and that begs the question, can we develop a theory of how small of a category you can possibly detect? So we used ideas from random matrix theory and singular value perturbation theory to essentially develop such a theory. Let's say that you have some total number of objects and some total number of features. So that's the size of your universe, so to speak. And then you have a small category consisting of K0 objects with KF features that are important for the category. If you're a feature within the category, then you have a probability P of appearing. If you're on the outside, then you have a probability of Q less than P appearing. So for what values of these quantities can you actually discover a category? And the final answer turns out to be simple. There's actually a phase transition in your ability to detect categories. This is the phase boundary. As long as the product of the number of objects and features times the signal-to-noise ratio is bigger than or equal to the square root of the size of your universe measured by this area, then you'll be fine. What's interesting is the square root appears here. So in the limit of large N, a vanishingly small category can be discovered even if it's buried in such noise. Okay? And the learning time is inversely related to this quantity, it turns out. So this is a natural definition of category coherence, and it's provably related to learnability in a neural network and provably related or inversely related to learning speed in a neural network. So believe it or not, the field of psychology never had such a quantity before that was provably related to neural network learning in this way. Okay. We can generalize this to hierarchically structured objects as well. I'll skip that in detail. But you can find all of this work in this paper, and we actually discover a whole bunch of other topics. For example, illusory correlations early in learning. Children will persistently learn facts that are false. For example, they'll always say that a worm has bones, despite the fact that they've never seen a worm with bones. They overgeneralize early on, and they restrict the specificity of the generalizations later on. And that shows up when we have mathematical formulas for that. They have changing patterns of inductive projection, and we have mathematical formulas that are consistent with the psychology literature for that, and so forth. I just wanted to end with just one final thing. How can deep recurrent neural networks navigate high-dimensional synaptic weight spaces without getting stuck? Okay. Let me just skip this slide. So, learning is often viewed as gradient descent on the synaptic weights of a neural network. Okay, so learning is like minimizing error over the space of all synaptic weights. Here's a cartoon picture. It turns out to be a cartoon picture of a protein folding landscape. But in this cartoon picture, there are local minima at very high error, and you might think that gradient descent would get stuck at local minima of high error. But of course, the way we think about geometry derived from learning and moving within a low-dimensional world is woefully inadequate for thinking about geometry of functions over high-dimensional spaces. It turns out for random non-convex error surfaces over high-dimensional spaces, local minima at very high error are exponentially rare in the dimensionality. Instead, saddle points proliferate. And we actually developed an algorithm that rapidly escapes saddle points in high-dimensional spaces. Well, first of all, we numerically showed evidence for saddle points in high-dimensional spaces of error landscapes. And let me just show you the algorithm. In the spirit of now talking about things that are useful at FQXi, I have 1 minute left. This is also kind of useful. So if you just do gradient descent, so this is error as a function of training time, and you just do gradient descent, the error drops off and it flattens out for two different learning problems, a deep autoencoder problem and a recurrent. It doesn't matter exactly what these problems are, but they are problems of interest to machine learning people. Okay, the error for gradient descent will flatten out. Okay, but we developed a new algorithm that can rapidly escape saddle points by finding negative curvature directions and exploiting them more efficiently. And so what happens is if you switch to our algorithm, the error suddenly drops again. Okay? So you might think that this plateau here is evidence that you're stuck in a local minimum, but it turns out it was illusory. There was a very small number of negative curvature directions from which you could escape. Stochastic gradient descent couldn't find them rapidly, but this other algorithm does. And you can read all about it in this paper here. Okay. So again, let me just there's a whole bunch of other stuff that of course I couldn't talk about, but I just wanted to end by saying there really is a role for sophisticated mathematics and physics that has played a role in advancing our field, in advancing physics, to yielding conceptual insight into deep learning. All right, thanks.